Okay, so let me start by thanking the organizers for putting together this nice conference and for giving me the opportunity to speak. I want to talk about work, mainly work in progress, that I've been doing over the last few months or so with Rajesh Gopakumar, Wei Li and Chang Pan, and also a paper that appeared earlier this year with Shuvik Datta, Wei Li and Chang Pan. And I should say right from the start that much of what I'm going to describe is largely motivated by work of Tomasz Prochacka, and I'll refer to it as I go along during the talk. So let me remind you about the sort of general setting I'm interested in. At a tensionless point in moduli space, string theory and ADS is dual to a nearly free conformal field theory. That just follows from the usual translation between the parameters. And the conserved currents of the free CFT correspond to the massless higher spin fields on ADS. And the idea is that in the tensionless string theory contains a sector of massless higher spin fields that account precisely for a Vasiljev-like spectrum, I having one massless higher spin field for each spin. So this is an old idea, and more recently, this has been, among others, there's one concrete realization of this idea in the context of ADS3, namely as you all know, the CFT dual of string theory in ADS3 crosses 3 cross T4 is the symmetric orbifold of T4, and the symmetric orbifold of T4 is, contains in particular a large W infinity algebra, this W infinity of n equals to 4 algebra. And this is the W algebra that appears in a family of dualities between the Vasiljev higher spin theories and conformal field theories. So in some sense, that's the CFT dual of the embedding of a higher spin subsector into string theory at this very special point in moduli space that is dual to the symmetric orbifold point on T4. So this is a concrete realization, and what we are trying to understand is that this is really like the analog of the free point of, say, super Yang-Mills in 4 dimensions. This is the lower dimensional analog of it. And in that case, it has proven very useful to think about this theory in terms of a spin chain where the integrability of the system becomes manifest. And what we would like to understand is what's the analog of this spin chain-like integrable description in the context of ADS3, CFT2. In particular, one thing one may want to understand is what's the relation between the Yangian symmetry, that's one of the hallmarks of integrability, to the higher spin symmetry that's manifestly present in the dual CFT. So we want to understand how does the sort of integrable spin chain part of the world and the higher spin CFT duality part of the world fit together. Now, one possible lead about where this Yangian symmetry may come from is that the actual string theory in ADS3 has an even bigger symmetry than just this W infinity algebra. And this is what Rajesh and I coined the higher spin square. So this is an algebra where you have a W infinity algebra, but the actual symmetry currents of the symmetric orbifold do not just contain this W infinity algebra, but it also contains infinitely many representations of this W infinity algebra. And you should think of this as being the level 0 part of a Yangian, and then this is the level 1 part, and then recursively, by taking commutators of D, you generate the full Yangian type symmetry. So that's one possible lead where you may hope to find a Yangian symmetry in this context. Now, in the following, I shall not actually discuss the n equals to 4 superconformal situation where we really understand the embedding into string theory, but I'll rather concentrate on the simpler bosonic duality involving the original bosonic higher spin CFT duality. And the reason for that is that it's technically much simpler. Eventually, we hope to be able to generalize what we've been understanding about this context to the supersymmetric setting, but we haven't quite reached that far. So in that case, the higher spin symmetry is this W infinity of lambda algebra, which you can think of as the minimal models WNK in the limit where the lambda parameter is n over n plus k, and the central charge of this W infinity algebra is the standard minimal model central charge. And the classical description in which you can match it to a higher spin description is the limit in which you take n and k large with the ratio n over n plus k being equal to lambda kept fixed. Now, what will be slightly important later on in this talk is that this W algebra is not actually parameterized directly in terms of lambda, but if you look at the structure of this algebra, what you realize it's if you construct its low-lying commutation relations, then it's uniquely characterized by the operator product expansion coefficient involving the spin 3 going to spin 4 field, as well as the central charge. And as a consequence, it's not directly parameterized by lambda, but it's parameterized by the value of this OPE coefficient. And if you decode how this OPE coefficient depends on lambda and c, what you learn is that there are actually 3 different algebras for a given value of the central charge that are isomorphic because they lead to exactly the same coupling constant for the spin 3, spin 4 field. So this will be important later on. Now, the other thing I should say is that in order to describe this Youngian symmetry that seems to be very closely related to this W infinity algebra, more easily it's convenient to add in a U1 generator. So we shall look at the algebra W1 plus infinity of lambda, which is W infinity of lambda plus U1. And this is really without much loss of generality, because whenever you have a U1 field, you can always coset it away. So every algebra that contains a U1 field plus the rest is isomorphic to a free U1 plus the rest. So in particular, this algebra will also depend on this parameter lambda, which is inherited from the lambda dependence of this W infinity algebra. Okay, so the paper I was alluding to at the beginning, the paper by Tomasz Prochacka that appeared at the end of last year, in December of 2015, he noted or observed or used previous results of other people to note that this W infinity, W1 plus infinity of lambda algebra is actually contained in a specific Youngian algebra, namely the affine Youngian of GL1. Now in the following, what I want to explain to you is how this embedding works on the additional further tests we have performed relative to what he has done, and it will also become clear that this is actually a very powerful technique towards describing the representations of the W infinity algebra, because the representations of the W infinity algebras will be labeled by plane partitions, so there's a neat way of understanding, say, the characters of these representations geometrically. So the affine Youngian, so these Youngian algebras tend to have different types of ways of being characterized. The version with which we've been working is one in which you think of it as an associative algebra that's generated by the generators Ej, Fj, and Psi_j, where j runs from 0, 1 up to infinity. And then you have to give a long list of commutation and anti-commutation relations. And the algebra is simply the associative algebra generated by this generate modulo all of the relations I'm about to write down. Now I'm going to give you the relations piece by piece. Eventually I will have written down all of them, but I don't want to write them down in one go because that will be somewhat overwhelming. So the first thing you should think about, or you should note, is that the Psi_j's you should think of as being zero modes. So they're the Cartan generators of this Youngian algebra because their commutator is equal to 0. And then the Ej mode and the Fk mode you should think of, but this is not to be understood totally strictly, as being the plus and minus 1 mode of a spin j plus 1 or spin k plus 1 field. I mean, this is to be taken with a grain of salt, as we shall see later on. This is not strictly true, but roughly speaking, these generators are the plus 1 modes of the spin fields of spin j plus 1 and k plus 1. And that makes sense because the commutator of a plus 1 mode with a minus 1 mode gives you a 0 mode. So this relation is makes some sense. Now the generators psi0 and psi1 are central. They commute not only with the other psis, but they commute with simply everybody. So they commute with the Ej's and they commute with the Fk's. So psi1 and psi0 and psi1 are central. And the way you should think about them is psi0 is the central term of the U1 and psi1 is the 0 mode of the U1. So because the 0 mode commutes with everybody, in each representation you can choose the 0 mode to take any specific value, and that will be to be thought of as the eigenvalue psi1. Now the higher generators psi2, with respect to psi2, all of these Ej's and Fk's are eigenmodes. The adjoint action is just the plus 2 or minus 2, and that basically means that you can think of psi2 as L0, and then this is 2L0, and then this is just the usual commutation relation with a plus 1 and a minus 1 mode. Now the eigenvalues of the other psi_j generators are determined recursively in terms of relations of this type. So this is one of the defining relations of the affine Youngian, namely this combination of commutators together with this anti-commutator here is equal to 0. And you can use this recursively to determine the eigenvalues of the psi generators on the E's. So this is the relation for the E's, and there's a similar relation for the F's that I haven't written out. Now, if you look at this relation, there are parameters sigma 2 and sigma 3 appearing. So these are three parameters that characterize the affine Youngian. So there's not just one affine Youngian, but there is a two-parameter family of affine Youngians characterized by the value of sigma 2 and sigma 3. And for the following, it will be convenient to parameterize these sigma parameters. Don't use them directly, but think of them as being expressed in terms of three parameters h1, h2, h3 that add up to 0, such that sigma 2 is all the bilinear products and sigma 3 is the cubic product. So sigma 3 is h1, h2, h3, sigma 2 is h1, h2, h1, h3 plus h2, h3. So this is how we're going to parameterize the parameters that appear in the defining relations of the affine Youngian. Now, as I said, there are additional relations that characterize the affine Youngian. So the additional relations are a relation involving two E's that are somewhat similar to the relation between psi and E. So this is now a relation involving two E's, and it's of the same sort of type. And then there's a similar relation for the F's. And finally, there are two Searle-like relations giving the repeated commutators of three E's, where you symmetrize over J1, J2, and J3, but note that you shift J3 plus 1 here, so this is non-trivial. This gives you Searle relations, and these you have to set to 0. And again, there's a similar relation for the F case. So this is the affine Youngian of affine GL1. There's a way of describing it more conceptually, but that's a sort of a hands-on way of making sense of this Youngian algebra. Now, what Prochatzka argued was that there is a relation between the conformal field theory, or the coset, or the W infinity algebra, which I may parameterize in terms of n and k, and this affine Youngian. And the relation is most easily expressed in terms of these h parameters. Remember, h1, h2, h3 add up to 0. As you can check, they do. And the sigma 2 is the pairwise product, and sigma 3 is the triple product. So Prochatzka claimed that the relation between the W infinity algebra at n and k and the parameters of the affine Youngian are given by this relation, where, as I also mentioned before, the psi 0 is to be identified with the central term of the u1, i minus n, and psi 1 is the eigenvalue of the u1 0 mode. So this will decouple once I've decoupled the u1 from the W infinity, because the u1 will just go along for the right. So what we've done is we have checked this identification by constructing the low-lying generators of W1 plus infinity in terms of affine Youngian generators. So what we've done is we've written down the modes of the W infinity generator. So this is the spin 1 field. This is the familiar Virasoro generator. And this is tries to be the one mode of the spin 3 field. So remember, I said earlier, you shouldn't think of this directly as the plus 1 mode of the spin 2 plus 1 field, but there are correction terms, and these are required in order to make sure that these generators sit in the correct SL2 representation generated by L1, L minus 1, and L0. Now, so this is more or less imposed upon you as the correct 1 and minus 1 mode, but then what you notice is that these generators do not come from local fields. And this is probably part of the general structure that a Youngian is a somewhat non-local construction. So what happens is if you try to calculate the commutators of these, they do not fall into the form that is predicted by the general conformal symmetry. But what you can do is you can adjust it by adding in correction terms. So the correction terms you add in look a little bit funny. They are not of any sort of typical local form, but they have to repair the non-locality of these affine Youngian generators. But once you do that, you get generators that then satisfy the standard commutation relation of your W infinity algebra. So we've done this for the spin 3 field, and we've done it for the spin 4 field. So these are somewhat lengthy computations because you have to work out what improvement term or correction term you need in order to make these non-local expressions local. And then once you've done that, you can calculate the operator product coefficient of the spin 3 going to spin 4. And what we find is that this is the version of this parameter n4 over n3 squared. That's how it's expressed in terms of the parameters of the affine Youngian. And then you compare this you compare this to the known formula that is holds for W infinity of lambda. And what you find is if you set H1, H2, H3 in the way Procházka proposed, and you set psi1 is equal to minus n, and you plug in all of these values, these two formulae precisely agree. So this, so Procházka had guessed this relation just by comparing the central charge, and what we've been able to see is that it really follows directly from the structure of the algebra, namely by computing the one coefficient that really characterizes the algebra and seeing its dependence on these parameters. Now, I should say that if you think about doing this recursively, what this tells you is that the W1 plus infinity generators are basically equal to these EJ generators modulo lower spin correction terms. And therefore, if you recursively do this, what this tells you is that that not just W1 plus infinity sits inside the affine Youngian, but the universal enveloping algebra of W1 plus infinity sits inside the Youngian. And in fact, there's a one-to-one way of rewriting every affine Youngian terms in terms of an element of the universal enveloping algebra. So this really demonstrates somewhat more pedestrianly that the affine Youngian is indeed the universal enveloping algebra of W1 plus infinity. I should also say we've checked other parts. We've checked there's a free fermion realization of the theory at lambda equal to 0. There's a free boson realization of the theory at lambda equals to 1, except the free boson doesn't give you the spin 1 piece. It only gives you the W infinity algebra, and correspondingly in that case you only need these generators of the affine Youngian to describe the free boson type generated with. But what's quite neat is that when you do this, so remember sigma 3 is expressed in terms of n and k in that way, and lambda is n over n plus k. So if you sit at lambda equal to 0, you take k to infinity, and if you sit at lambda equals to 1, you take n to infinity. In either case, you take sigma 3 to 0, because it goes like inverse square root of n times k. But while sigma 3 is 0, sigma 3 psi 0 goes to 1 in the lambda equals to 1 case, because this is just this expression. So when you take n to infinity, this goes to 1. And what this means is that in this funny anti-commutator that I showed before, this term that you would naively think to drop out at sigma 3 equal to 0 contributes for the j equal to 0 term, because this combination is equal to 1. And if you include this, then it matches perfectly. But you really need to take care of this subtlety, but then the free boson description sits perfectly inside this W, inside this affine Youngian. Now, the other thing that's quite neat is that this triality symmetry I mentioned earlier. So I said that the algebra isn't really uniquely characterized by n and k, but there are different versions that lead to isomorphic algebra. So you may ask, what's the incarnation of this symmetry on the level of the affine Youngian? And so the transformations of the triality symmetry are generated by these two transformations. And when you translate the first one into the action on these h parameters, what you see is that simply exchanges the role of h1 and h2, but doesn't do anything to h3. And as a consequence, it leaves sigma 2 and sigma 3 invariant, because these are just all the bilinear or trilinear combinations of the h's. Now, the second transformation is a little bit more subtle, because if you just do it on the nose, you get some garbage which isn't equal to any of the h's. But you also notice that psi 0 got rescaled in the process, and there's something I didn't tell you before. There's a scaling symmetry inside the affine Youngian. If you had been counting parameters, you would be a little bit worried that I had so many parameters. You can rescale the psi's, the e's, and the f's, and in the process rescale the alphas in that manner. So if I rescale psi 0 to bring it back into the form of minus n, what this does is that it means that the second transformation just leads to the exchange of h2 and h3. So what this means again is that the affine Youngian parameters are unmodified, but this is quite nice because the triality symmetry acts like the permutation group on the three labels h1, h2, h3. One generator is the permutation of h1, h2. The other generator is the permutation of h2, h3. Now I should also, as a side comment, say that this is there is another description of these Youngians or algebras that are believed to be very closely related, the so-called SHC algebra, and they look a little bit like the higher spin square, and that fits also together with our picture, but in view of time I shall skip that comment. Now the other thing I wanted to explain to you is that leads to a very neat way of describing the representations of this W infinity or W1 plus infinity algebra. And the idea is that the maximal degenerate representation of the affine Youngian and hence of this W1 plus infinity algebra are described by plane partitions. So plane partitions are boxes that you stack in the corner of a room in such a way they don't fall down in any of the possible directions. And the idea is that the different representations are labeled by the different asymptotics in the three directions of your room, whereas the different states in a given representation correspond to the different box configurations. So you fix the asymptotics, and then you draw all the plane partitions that are compatible with these asymptotics, and then each such configuration corresponds to one state of your corresponding representation. And the L0 eigenvalue, the power of Q, is just the number of boxes. And you can see very nicely that that's a representation of the affine Youngian, because the E generator basically adds a box, the F generator subtracts a box, and the Psi generator acts diagonally. So obviously, for the trivial asymptotic, that just gives you the famous McMahon function. That just describes the usual box stackings in the corner of a room. And as people have known for a long time, that's equal to the vacuum character of the W1 plus infinity algebra. So that just tells you that the trivial asymptotics just gives you the vacuum character of this algebra. Now, the non-trivial representations are labeled by their asymptotic behavior. So, for example, here's a generic case where along the z-axis you have this asymptotic behavior, along the y-axis this, along the x-axis this. And then there is a configuration with a minimal number of boxes that describes the ground state of this representation. And then you simply count how many boxes can I add to this configuration. So here the brown boxes are the descendants that I've added. So this is 2, 4, 6. This is a level 7 descendant. And the character of this representation is simply the number of box configuration with 7 additional boxes relative to the minimal configuration. So this gives you a neat way of describing these representations. And what this really tells you is that the affine Youngian has a nice action where all of these zero modes are diagonal, unlike the usual W infinity algebra, where the action of the zero modes is very complicated. So in particular, the eigenvalues on the ground states can be written down in this form. And what you observe is that they really depend on H1, H2, H3 in the way that you count the position of you take the product over all the boxes, you take the X component, the Y component, and the Z component of the corresponding box. You multiply it by H1, H2, H3, and that's the coefficient that appears inside this function. And what this tells you in particular is that the triality symmetry just permutes the asymptotic behaviors, because the triality symmetry exchanges permutes H1, H2, H3, but H1 describes the x-axis, H2 the y-axis, H3 the z-axis, and therefore the triality symmetry will just permute the different asymptotic regions into one another. So this makes very nicely sense of this old triality observation of the paper I wrote with Rogers a few years ago, in that the coset representation, the standard representation of this WNK algebra, are labeled by those asymptotic regions where the Z component, say, has trivial asymptotic. But then, using this triality symmetry, you are led to conclude that there is a third representation that has a non-trivial asymptotic, and this is indeed comes out exactly right with the correct character, the correct eigenvalue for all the charges, etc. So it brings this family of these representations of this W infinity algebra nicely together. So in particular, this provides a powerful technique of the calculation of this coset or W infinity characters. In principle, you can calculate using branching functions, but that's not a super easy calculation to do. But in terms of these plane partitions, you can just have fun drawing boxes and counting how many possibilities you have. So it tells you very directly what the low-lying representations are. And recently, we used this in this paper I was referring to before in order to identify the representations that correspond to the twisted sector. And so these are representations of this kind, and one could really guess that they had to be of that kind, because that gives you the correct character when you count boxes. So let me summarize, given the fact that I'm out of time. So what we've shown, and as I keep reiterating, this goes back to an observation of Prohatzka, is that the affine Youngian of GL1 captures this W1 plus infinity symmetry. In fact, it seems to be isomorphic to the universal enveloping algebra of the W1 plus infinity symmetry. The triality symmetry, that's a little bit obscure from the point of W infinity, has a very neat action on the representations in terms of exchanging the asymptotic direction. And among other things, this is a powerful method for the calculation of characters. And obviously what we would like to do is we would now like to take this affine Youngian and try to understand the spin chain and compare it to the spin chain proposals for what people have proposed the spin chain description of the ADS3 situation to be. But the first step we probably have to do in order to really make contact with the work of these people is that we have to make it supersymmetric, probably n equals to 2 and then n equals to 4 supersymmetric. And then the hope will be that we will be able to make contact with the spin chain description of string theory in ADS3 cross S3. Thank you.
Thank you. Any questions?
I have two questions. Two quick questions. So this partition was kind of refinement in the way of skew partitions. First, I wonder if they play any role in your presentation. And second question is, when triality acts in terms of n and k, n ascend to non-integer value, does it cause any difficulty or no one worry about?
Well, I mean, so to answer the second question first, about which I'm more confident, is that these WNK algebras, at the end of the day, they only depend on the parameter characterizing the 3, 3, 4 coupling constant. And that's some expression in terms of n and k, and the fact whether n and k are integers or not is pretty irrelevant. What happens if n is an integer is that the algebra actually truncates and it contains an ideal, and if you divide out by it, it just becomes a Wn algebra, but this algebra makes sense for any value of n and k, and they needn't be integer in order, at least for the algebra, to make sense. Whether the representation theory is unitary, etc., is a different matter, but on the level of making sense of the algebra, that's not a problem. Now, regarding your refinement, I'm not quite sure what you mean. Do you mean adding in some additional quantum number, or do you think of Q deforming it further to get Q Virasoro rather than Virasoro?
Well, if you choose a direction in rather a plane in this three-dimensional space where partitions be, so then one can start distinguishing and think of a three-dimensional partition as collection of two-dimensional partitions, and that's the definition of the skew partition.
Ah, okay, yeah. So that you can do, and that will probably correspond to some U1. I mean, you can add into your trace some additional zero mode, and that will pick up things like that. Yeah. But I mean, here it's quite nice that you're not deciding to split up the plane partition in a set of Young diagrams, because that's not compatible with this triality symmetry, where you really exchange all three directions.
Is there a physical generalization where you have n copies of the affine Youngian? Is there any way to generalize this? You have n copies of that Youngian. The reason for my question is that you have n copies of the affine Youngian, you get this W algebra that appears in the HD correspondence.
Well, I mean, actually, I mean, even this algebra, I mean, so as I was trying to allude to, but I was very quick on that slide, is that there is this SHC algebra. And the SHC algebra has appeared in attempts to prove the AGT correspondence. And what you can show is that the SHC algebra is isomorphic, or embeds into the universal enveloping algebra of certain Wn algebras. And for that, this SHC algebra seems to be isomorphic to this affine Youngian, and I don't think you need additional copies of the affine Youngian for this to work. So the parameter n is somehow hidden in here. It's not that you need n copies in order for that to work.
Mollick and Openikoff, they showed that they had n copies of the affine Youngian, and that's isomorphic to the W algebra related to SUN. So that's the basis of my question.
That may be so, but I think if I understand correctly, Schiffman and Vasaro have shown that also the SHC algebra, which by all accounts I believe to be isomorphic to the affine Youngian, is also isomorphic to the universal enveloping algebra of WNK. So you have to choose the parameters of the SHC algebra correctly. So you don't need to enlarge this description to see Wn. You may enlarge it, but you can already see it on this level. But maybe you can discuss in private.
Okay, I think we should stop now. So we have a break and we resume at 4 o'clock. Let's thank our speakers again.